subscribe to our YouTube channel, Joy Learning TV.
Hello, it's good to see you again on Joy Learning TV. It's Senior High School R, and I'm happy to come your way this time too. Anekpabi Albert is my name, and I'm going to take you through physics for SHS 1. This is our second lesson on kinematics, and we'll go straight away, try to solve some questions on what we did in the first lesson. So let's get on board, get your pens and your calculators ready, and let's do some calculations. First question. It says, what is the difference between rotational motion and circular motion? We've come across the types of motion in our first lesson. Now we have been asked to tell the difference between rotational motion and circular motion. So we can say that in rotational motion, the body describes a circular path and moves about an axis within the body itself. So when the body is undergoing rotational motion, 1, it will describe a circular path. That is true. 2, the body will move about an axis, and this axis is found within the body. An example, the motion of the blades of a ceiling fan. So that is an example of rotational motion. But in circular motion, the body only describes a circular path and may or may not move about an axis. And even if there's an axis, it is outside the body. So an example, a car moving in a runabout or a vehicle moving in a runabout, it will describe a circular path, but there's no axis within the body about which the vehicle is moving. So that is the difference between rotational motion and circular motion. Our second question, it reads, a bicycle rider rides at a speed of 5 meters per second. What does this mean? That's quite interesting. So we have a rider moving at a speed of 5 meters per second. What is the meaning of that? In our previous lesson, we learned that speed is the distance traveled per time. So if the rider's speed is 5 meters per second, in that we have meters and we have second. So this means that in every second, the rider travels a distance of 5 meters. So this rider travels a distance of 5 meters in every second. I hope that is well understood. Good. Question number 3. It says a train takes 2.5 hours to travel from Obuasi to Dunkwa. I hope some of you are in Obuasi watching us now, and some of you may be in Dunkwa. So we are in your towns this time. 208,000 meters apart. Calculate the speed of the train in I, meters per second, and then II, kilometers per hour. So to start with, we have to put down our parameters. Then look out for those ones that are not in the SI units. Then we change. You need to do that. So we are told that the train takes 2.5 hours. So that is the time. So we find the time. T is 2.5 hours. Don't forget 2.5 is the same as 2.5. Then the distance has been given to us. So distance, the symbol S, is 208,000 208,000 meters. And then we are asked to find the speed. So we need the speed in meters per second. But our time is in hours. So we have to change the time to seconds. So in I, we have speed in meter per second. So we change the time. We have time t to be 2.5 hours. When you multiply that by 60, it will take it to minutes. So times 60. But we need it in seconds. So we multiply by another 60. So times 60. And that will give us 2.5 times 60 times 60. 9,000 seconds. So our time is now in seconds, 9,000 seconds. And our formula says speed is equal to distance over time. I've already explained that distance, I'm using s to represent it. And then time, I'm using t. So I don't need to write everything in full again. So I have to put in my values. I'm going to get the distance, which is 208,000 over the time, which is 9,000. And that will give us 23.11. The unit for speed is meter per second. So we are asked to find that in meter per second. And that is not too difficult for us. So we move on to the next part. We are asked to find now the speed in kilometers per hour. So for I, we need the speed in kilometers per hour. We already have the distance in meters, so we'll change to kilometers. So the distance is 1,208. So 208,000. We divide by 1,000 to change it into kilometers. And that gives us 208 kilometers. Kilo is a prefix, which is 10 to the power 3,000. So 208 kilometers means 208 times 1,000 meters. And it goes back to 208,000 meters. Good. So now we have our speed to be equal to still the distance over the time. And that gives us the distance will be 208 kilometers. And the time is 2.5 hours. 2.5 hours. And that gives us 83.2 kilometers per hour. I believe you've been able to try this one too. You've been able to follow it, and you should be able to do or answer similar questions like this. We can move on to the fourth question. A vehicle travels 3.0 kilometers due east to a town X, then 4 kilometers due north to another town Y. Find the I, total displacement, then I, total distance covered. Then B, if the total time for the journey is 1 hour, find the velocity of the car or the vehicle. So this one too, we will start by putting down our parameters given in the question. We have the vehicle traveling 3 kilometers due east. So if I draw, trying to get my north and my south, and I have the east somewhere here and the west. So 3 kilometers due east, it means I'm here and I'm going towards the east this way. So 3 kilometers. Then to a town X. So I have X there. Then it moves 4 kilometers due north to another town Y. So from where it ended the first motion, we go due north to another town Y, which is 4 kilometers. So let's say the body was at O, it moved to X, and then moved from X to Y. So we are asked to find the total displacement. The displacement, as we have already learned, is the distance between the initial position of the body and the final position of the body. So it was at O, now it's at Y. So that distance from O to Y becomes our displacement. So let me say D is that distance. And the diagram you can see is a right angled triangle with the displacement part or portion being the hypotenuse. So we are going to apply Pythagoras theorem to find that hypotenuse, which becomes our displacement. So AI, total displacement, from the diagram, that's D. So I'm going to apply the Pythagoras theorem. It says hypotenuse squared is equal to the opposite squared plus the adjacent squared. And now we want to find D. So D squared will give us 4 squared will be 16 plus 3 squared, which is 9. And 16 plus 9 will give us 25. So D squared equals 25. We want to find D. So we find the square root on both sides. So that we have D giving us square root of 25. And your answer will be 5 kilometers. Our answer is in kilometers because the values of the distances given in the question have units in kilometers. So our displacement becomes 5 kilometers. Then we are asked to find the total distance covered. Total distance. Let's see, S. From the previous diagram, the body moved from O to X and X to Y. From O to X is 3 kilometers. From X to Y, 4 kilometers. So our total distance covered becomes S equals 3 plus 4. And that gives us 7 kilometers. That becomes a total distance covered. Then we are asked again to find the velocity of the car if the total time for the journey is 1 hour. So you're going to find the velocity of the car. So for the B part, I have to find velocity, which is V. Now we know that the formula says velocity is equal to the displacement over the time taken, the rate of change of displacement. That gives us velocity. So V will give us the displacement over the time. So we have to find the velocity, but it should have displacement and then time. And the time must be in seconds because the unit is meter per second. So we give it a time to be 1 hour, which we have to change to seconds. So 1 hour times 60, that gives us 60 seconds. Then we go back to the formula velocity equals displacement from what we have done. We got the displacement to be 5. So 5 on the time to be 60. So 5 divided by 60, and that gives us 0.083. So 0.083 meters per second. That becomes the velocity of the car or the body. I hope by now you've been able to try your hands on these, finding the velocity, finding the speed, and finding the displacement. So you try and get some past questions and then practice more so that you get to understand it better. So we move on to what we really want to do for today's lesson, and I'll start with acceleration. You could be in a vehicle, and then all of a sudden the driver starts moving very fast. You can feel the wind so strong. The vehicle is moving very fast. What is the driver doing? The driver is stepping on the accelerator. And so we say the driver is accelerating. So what do you mean by acceleration? We mean acceleration is the rate of change of increasing velocity. The rate of change of increasing velocity. In other words, acceleration is the change in, so note, change. The change is very important. The change in increasing velocity with time. And increasing here too is important because it would happen that the driver will do something and the velocity will be changing, all right? But it will not be increasing. It could be decreasing. In that case, it will not be acceleration. So acceleration is the change in increasing velocity with time. Therefore, mathematically, we can say acceleration is change in velocity on time. So we have known initial velocity, we've known final velocity. So if you want to talk about change in velocity, then it becomes the final velocity minus initial velocity. The final velocity is v, initial velocity is u. So you have v minus u, giving us the change in velocity over time. There again, we'll look at the unit for acceleration. Now, we have said that acceleration is the change in increasing velocity with time, and it's change in velocity over time. So for this part, the unit will be meter per second. And for this part, the time, the unit is second. So together, it gives us meter per second times another per second, because this second here, which is the denominator, it goes up to become s minus 1. And that gives us meter per second squared. So the unit for acceleration is meter per second squared. So what does this mean? Let us try to see if we can explain this. A body moves with an acceleration of 18 meters per second. A body moves with an acceleration of 18 meters per second. So what does this really mean? Note that in 18 meters per second squared, you have meters per second and another second. So if a body moves with an acceleration of 18 meters per second squared, then it means that in every second, the velocity of the body increases by 18 meters per second. That is quite technical. But we should be looking at what we're talking about here. We're talking about velocity, we're talking about time. And so the units of these will play, or will come to play. The body is moving with an acceleration of 18 meters per second squared. Acceleration comprises of velocity and time. So in this 18 meters per second squared, there is velocity and there is time. So it means that in every second, that is the time aspect, the velocity of the body increases by 18 meters per second. So you see that this 18 meters per second becomes the velocity because the unit is meters per second. And 1 second becomes the time. Very important. So you need to understand these things. We can move on to uniform acceleration. When do we say a body, a vehicle, a car is moving with a uniform acceleration? We have looked at uniform speed, uniform velocity. So by now, uniform acceleration should not be too difficult for us. This means that the rate of change in increasing velocity is constant. So the body's velocity changes equally with equal time intervals. When a body is moving such that its velocity is changing equally with equal time intervals, we say the body is moving with a uniform acceleration. Let us look at a graph for uniform acceleration. You can recall from our previous lesson that the graphs are defined by the labeling of the axis. So we're going to draw graphs for uniform acceleration. Then the axis will comprise of velocity and time, because acceleration is the change in increasing velocity with time. So I'll pick my first axis, velocity in meter per second. Second axis, I have time in second. So velocity against time, and it's uniform. So this way. In this graph, you have the graph beginning from the origin. Let's see. O. So this tells me that this body began moving from rest. We have learned that when a body starts moving from rest, it means its initial velocity is 0. So this is a uniform acceleration graph. When the body starts moving from rest, what if the body had an initial velocity? So it didn't start moving from rest. What do we do? That the graph can show that. So in that case, you can pick this axis for velocity. So v in meter per second. Then this axis for time in second. And this time, you will not start from the origin. So it means that in this particular graph, the body had an initial velocity u. So the graph is not beginning from the origin here, rather there is an initial velocity. So both graphs are for uniform acceleration. Then, if we find the slope of these graphs, what do you think the slope will represent? We said the slope is also defined by the labeling of the axis. So if you look at the axis, we have velocity against time. And velocity, the time, is acceleration. So the slope of a velocity time graph represents the acceleration of the motion. Very, very important. The slope of a velocity time graph represents the acceleration of the motion. Then, it is not every body or every vehicle that would be moving all the time with a uniform acceleration. So it can happen that now the vehicle is moving with non-uniform acceleration. What do we mean by that? Then that means that the rate of change in increasing velocity of the body is not constant. So the body's velocity, its change in velocity with time, is not constant. In that case, then the body is moving with non-uniform acceleration. We can look at the graphs for non-uniform acceleration. So in this case too, we will label the axis velocity against time. So this, that. Velocity in meter per second against time in second. Then it's non-uniform. So it's no more be a straight line. This time, it will be a curve. So this is a graph for non-uniform acceleration. In some other times, you could have the curve being a little more curvy. So we could have something like this. Still velocity against time. So velocity in meter per second. Then time in second. It could be like this. So this one too, the body is moving with non-uniform acceleration. The labeling of the axis is velocity against time. Now, because the body is not moving with a uniform acceleration, acceleration is non-uniform, we can't really tell the acceleration of the body because it changes, it varies from time to time. But we can find acceleration at a point in time in the motion or during the motion. And that acceleration at a point in time for a body that is moving with non-uniform acceleration is called the instantaneous acceleration. That means the acceleration at an instant, at a point in time as the body travels. So, because acceleration is not uniform, we can't just calculate, but we can pick it at a point in time. We can't pick it for the whole journey, but at every point in time, we can pick the acceleration there. And that acceleration becomes what they call the instantaneous acceleration. Instantaneous acceleration. Then there's another thing that is quite interesting. We can have a velocity time graph, and you not have a curve that is moving maybe upwards. You not have a straight line also moving upwards. But we can have a horizontal line. That's what we call the uniform or the constant velocity on a velocity time graph. So we are saying that if a body moves with a constant or uniform velocity, its acceleration is zero. In other words, what we mean is this: a body moving with a uniform or a constant velocity does not accelerate. And we will look at that one in a jiffy. Why are we saying so? Because the initial and final velocities of the body become the same. They are equal. So the body began moving with maybe a velocity of 10 meters per second. It ends the motion with same velocity, 10 meters per second. So you see the change in velocity becomes 10 minus 10, and that becomes 0. So in effect, the total acceleration of the body becomes 0. And so we say that the body moving with a uniform or a constant velocity does not accelerate. Let's look at the graph for uniform velocity on a velocity time graph. So as usual, I'll draw my axis. And I'll label velocity, time in second. This time, the graph looks like this. So this graph is a constant velocity graph on a velocity time graph. And the labeling of the axis is velocity against time, like this, which is supposed to be acceleration. But in this case, we are saying that the body is not accelerating. Why? Let us try to do some illustration. Let me pick this new graph. Velocity in meter per second, time in second. Now, we still have a horizontal line this way. Let's try and put in some values. So 0, maybe 2, 4. Let's say 6. And let's say that we have 10 here. So from this graph, the velocity is 10 meters per second at time t equals 0. Now, at time t equals 2, if you want to find the velocity, you go up from 2. So you move from 2 up, and you read on the velocity axis, and it is still 10. At time 4 seconds, you go up to the graph, you read the velocity on the velocity axis, it is still 10. At time 6 seconds, you go up to the line, you read the velocity, and it's still 10. So although the time is progressing, the time is increasing from 0 to 2 to 4 to 6, the velocity remains at 10. And so we are saying that this is a constant velocity graph. A constant velocity graph. The velocity is constant. So constant velocity. And another name for constant velocity, we are saying, is zero acceleration, because acceleration will be the change in velocity over time. So if you are looking at time, maybe 0 to time 6 seconds, 6 minus 0 gives us 6. Then change in velocity will be the final velocity here, which we read this way, minus the initial velocity also this way, which is 10. So it becomes 10 minus 10 over 6 minus 0. And it becomes 0. And so we say constant velocity or zero acceleration. Constant velocity or zero acceleration. So take note of this. When a body is moving with a constant velocity, it does not accelerate. Its acceleration is 0. We've been talking about acceleration, fine. Vehicles, cars don't always speed. There could come a time when a car is moving at a very high speed, then it will have to stop, or it will have to decrease the speed. When do you think these things can happen? Maybe a perfect example is when a car is approaching the traffic lights, and then the driver can see amber, the yellow light blinking. That means that be getting ready to stop. So when you are driving and you come across the traffic lights and you see amber, you don't rather speed, you prepare to stop. And how does the driver prepare to stop? What does the driver do? The driver will start stepping on the brakes. Very important. So as you step on the brakes, now the car will start moving slowly. The car starts moving slowly. And in this case, we say the car or the vehicle is decelerating. It's decelerating. So we can look at what we call deceleration or retardation. So another name for deceleration is retardation. And this time, deceleration or retardation is the rate of change. So you see change is here again in decreasing. This time it is not increasing, but it's decreasing velocity. So the rate of change in decreasing velocity is what we call deceleration. Now, deceleration is the opposite of acceleration. So the driver is stepping on the accelerator, the vehicle is moving very fast, we say it is accelerating. Now, the driver is stepping on the brakes, the vehicle will now be slowing down, we say the driver or the vehicle is decelerating. Now, deceleration is a negative acceleration or a negative of acceleration. It is very, very important to take note of this. So when it happens that you are supposed to work out, you are doing some calculations, and then you are told that a vehicle is, or a body is decelerating at a particular kind of value, that value given to you should be negated as you work, because a deceleration is a negative acceleration. Take note of that. And in this case too, the SI unit for deceleration will still be meter per second squared. Meter per second squared, because it will still be the change in velocity over time, like the previous one that we looked at. So we can also have a graph of uniform deceleration. You can also have a graph of non-uniform deceleration, which we will look at pretty shortly. So, if we should tell you that a body moves with a retardation here is the same as a deceleration, so it's the same thing, of 20 meters per second squared. What does this mean? What does this mean? This means that in every second, the velocity of the body decreases by 20 meters per second. 20 meters per second. So the body moves with a retardation of 20 meters per second squared. This means its velocity is decreasing by 20 meters per second in every second. In every second. That's what we mean by a body moves with a retardation of 20 meters per second squared. We can have uniform deceleration. In this case, the rate of decreasing velocity is constant. So the rate at which the body's velocity decreases is uniform. The body's velocity decreases equally with equal time intervals. Then we say the body is moving with a uniform deceleration. We can quickly look at a uniform deceleration graph. So we pick up the axis, still velocity in meter per second. Velocity in meter per second. Then time in second. And this time, you are saying uniform deceleration. So the velocity is high, or it was high, and it is gradually decreasing. So we pick it from up there, and it comes down. So this becomes a graph for uniform deceleration. A graph for uniform deceleration. We can also look at non-uniform deceleration. Non-uniform deceleration. This is when the rate of decreasing velocity is not constant. When we say a body is moving with a non-uniform deceleration, then it means that the body's velocity will be decreasing with time, but it decreases differently at different intervals. The rate at which the velocity is decreasing is not constant. So just like we drew a graph for non-uniform acceleration, we can get the same or similar graph for a non-uniform deceleration. So as usual, we will label the axis velocity in meter per second, time in second, like that. And this time it is a deceleration which is not uniform. So like that. And that gives us a graph of non-uniform deceleration. So you can just guess, if you want to find the slope of this graph, we just find it at a point or at an instant as the body travels. And what will be the name? Your guess will be as good as mine. It will now be an instantaneous deceleration. Instantaneous deceleration. I think we have gone through enough of theory of this acceleration and deceleration. Let us see how we solve some questions and what we've done so far as we prepare to round up the lesson. So question number 1, very interesting one. A body starts from rest. So you have to recollect your previous knowledge, what we learned. When you said a body starts from rest, what does it mean? You have already been given a value or a data in the question. And accelerates uniformly at 8 meters per second squared for 2.5 minutes. Then we are asked to calculate the final velocity. So let's put down our parameters. From what we have, a body starts from rest. When a body starts from rest, its initial velocity is 0. So initial velocity is u, that is 0. And accelerates uniformly at 8 meters per second squared. So the acceleration A is 8 meters per second squared. Now, for 2.5 minutes, so the time t is 2.5 minutes. You know that the SI unit for time is second, so we change the 2.5 minutes to seconds. So we multiply 2.5 by 60, and that gives us 150 seconds. Then you're asked to find final velocity. So I'm saying final velocity is v. So final velocity is v. Our formula says acceleration is change in velocity per time. So A will give us that minus that, final velocity minus initial velocity over the time taken. It's either you make V the subject and you find it, or you put in the values and you work. As you go along, you'll be able to find V. Acceleration is 8. You don't know V. Initial velocity U is 0. Our time is 150. This will give us, that gives us 8 is equal to V on 150. We want to find V. So V will be equal to 8 times 150. And that gives us 1,200 meters per second. So take note of this. Very often, students will write the answer, but they will leave the unit out. Without meters per second as the unit, it ceases to be a velocity. Good. The next question, question number 2. A cyclist decelerates from 10 meters per second to rest in 5 seconds. What is the deceleration of the cyclist? Now, be careful of this question or questions of this nature. We are being told of a deceleration. Decelerates from a value. But the value given to us, the unit attached to it is meter per second, which is a velocity and not an acceleration or even a deceleration. Then to rest. So just as we learn, when a body moves to rest, it means its final velocity is 0. So the first velocity given to us in the question, which is 10 meters per second, becomes the initial velocity. So your initial velocity becomes 10. So for our solution, we have initial velocity, which is 10 meters per second. Then the final velocity is 0 because the body came to rest. And the time is 5 seconds. And we are asked to find the deceleration. So I'll say deceleration is maybe A. And the formula says our A is the change in velocity. So final velocity minus initial velocity over time. So A will give us, the final velocity is 0, initial velocity is 10, and the time is 5. So A will give us minus 10 on 5, which will be minus 2. Then don't forget the unit, meters per second squared. So it confirms what we said earlier on, that deceleration is a negative acceleration. So when you find deceleration in the question and your value is not a negative value, then there's something wrong somewhere. Let's look at the last question. Then we will say bye-bye for now. We are told that a motorist decelerates from 12 meters per second to 5 meters per second with a deceleration of 0.8 meters per second squared. We are asked to find the time for the retardation. So we can look at the suggested solution. We are looking for the time. Now, what we have here is 12 meters per second the deceleration began from 12. So that becomes our initial velocity. Then to 5 meters per second, that becomes the final velocity, which is v. With a deceleration, so we have a to be 0.8 meters per second squared. But don't forget that deceleration is a negative acceleration. So I'm going to negate this value 0.8 to be minus 0.8 meters per second squared. Then you are asked to find the time. So our time, which we don't know, is t. We go back to our same formula which says the deceleration will be change in velocity over time. So that will give us minus 0.8 is equal to the final velocity, which is 5, minus the initial one, which is 12, on the time which we are looking for. So what do? If you just cross multiply, you're going to get minus 0.8t equals 5 minus 12. And 5 minus 12 gives us minus 7. So the negatives will cross out that way. And you're going to get t, our time being equal to 7 over 0.8. And 7 on 0.8 gives us 8.75. 8.75. The unit will be second because of the time, because it is the time. So I believe you have been able to solve some of the questions on your own and you have enjoyed the class. I hope to come your way another time as we progress in our study of kinematics. Once again, Anepabi Albert is my name. You can call me Pius. And I wish you all the best. Keep doing what you've been doing and be consistent at it. So bye-bye for now.
Subscribe to our YouTube channel, Joy Learning TV.